nobody's.
Kind of low down.
I just know it was Alvin and
Okay, let's go ahead and talk about timers. So we have a variety of different types of timers. Originally the timers were mechanical, but extremely inaccurate. This is by virtue of a spring wound timer, kind of like an egg timer in the kitchen. Is what they used in the X-ray system. But they developed these timers that worked off of the incoming line voltage, alternating current, alternating current. So we talked about this, and alternating current alternates, it goes back and forth 60 times per second. Right? So it's back and forth, back and forth, back and forth, really quick. So what they did was they developed these timers that worked off of the incoming line voltage, and where, let's say in this example, where the voltage, the wave started and where the wave stopped was the maximum, well, not really the maximum exposure, but that's the more like the minimum exposure that it could make. Okay. So it would count the cycles, and you could initiate, and some textbooks will call that interrogation, which is just a horrible word. Sounds like, torture. But interrogation time, and even worse than that, would be what you refer to as extinction time. Yeah. So I kind of go on with the Auschwitz thing going here. Interrogation time, extinction time. It begins, it ends. All right. So this is what we refer to as synchronous timer because it was synchronized to the voltage waveform. So our exposures then on these type of machines could be multiples of 1/60th of a second, right? So if you got a single waveform, that's 1/60th of a second because there's 60 waves in 1 second. Does that make sense? Okay, but remember that our X-rays, we want to create X-rays. This is kind of jumping ahead to voltage rectification just for a second, but we want X-rays to go from the negative side of the tube to the positive side of the tube, from the cathode to the anode. The anode, as you saw, was a big hunk of metal, right? Sturdy, thick, hard to melt. But this over here is a little skinny wire, right? Still, in the cathodes that I passed around earlier in the semester, what did you see? They're old X-ray tubes, non-rotating anodes. What did you see in the anode? You remember? Some of them were melted, right? Remember seeing that? I need to pass them around again. But you can melt the anode. You apply enough heat from the cathode to the anode, you can melt the anode. That's a big hunk of metal. So if you send electrons from a big hunk of metal to a little skinny wire, do you suppose that the same thing might happen? Might it happen even easier? The answer is yeah. If you can break the big chunk of metal, certainly you can break that little skinny chunk of metal. So you want electrons to go from cathode to anode, but you don't want them to come back across. So we've got a circuit that does a couple of things. It prevents electrons from coming back this way. Okay, our problem, if anytime you have a problem, you've got a solution, and a synonym for solution is that you're going to do what to the problem? Fix it. Another one would be rectify the situation, right? So we have a rectifier circuit. So let's talk about that, and then I'll tell you what we're going to use for rectification. Okay, so after the voltage comes out of the secondary side of the high voltage transformer, it's going to go into the cathode and anode into the X-ray tube. Okay, so we have to have a complete circuit. You remember talking about the circuits and the grounds and the complete circuit. Otherwise, we have short circuit, right? So we have to complete the circuit. So it's going to go into the cathode into the X-ray tube, out the anode into the X-ray tube for this example. But what we want are electrons going in that direction, but we want to prevent them from coming this way. So if we could set up a situation where we could send electrons out of the high voltage transformer in one direction, and when they reverse flow and go in the opposite direction, we'll put a stop sign. How many sides on stop sign? I think it's not enough, but anyway, we put a stop sign right there. The electrons can't go that way. They can't get to the anode. They can't jump across. Okay, essentially what we've got is voltage rectification. The electrons can go from here to there, but they can't go from here to here. Does that make sense? So we had a problem. The problem was reverse current. The solution was voltage rectification. Okay. So what we're going to do, though, is instead of just putting up a stop sign, what we're going to do is we're going to give it a way to make a U-turn and go back in the opposite direction. So now we've got two pulses going in the same direction. Okay, again, I'm going to draw this out a little bit better here in a bit. I just want you to be familiar with this at this point. So not only do we rectify, the definition of rectification is taking alternating current and making pulsating direct current. Okay, so we went from, before we did this, we went from this, right, that's alternating current. We went from that to this. Is that wasteful? It's all going in one direction, right? So that's, we've accomplished what fundamentally we needed to do, and that was to prevent this. We've done that. But where's all that, you know, the portion of the voltage waveform go? It cuts it in half, right? We're only using half of our electricity. Is that wasteful? Okay. You flip the lights on in your living room, then you leave the room. That's what you got, right? Just throwing money out the window, pretty much. So if we can give this a different direction to go, now we can take that negative side and we can pop it up to the top like that. Okay. So now what we've got is not just the rectification so that we prevent the reverse flow, but we've taken that negative side and we're using it too. So still direct current is still pulsating direct current, but I have exactly doubled the output of my X-ray tube. Instead of sending one pulse across every 60th of a second, I'm going to send one pulse across every 120th of a second, or two every 60th of a second. I'll double the output of the X-ray tube. Still pulsating, still direct current, but I've doubled the output of the X-ray tube. So what we've got is not just rectification, but a flipping of the negative side of my voltage waveform up to the positive side, so I double the output of my X-ray tube, make it more efficient. Okay? So then, how many pulses do I have per second now? I have two per cycle, but I've got 2 times 60, which is 120 possible pulses. Okay? So now let's go back to the synchronous timers. Now synchronous timers can work off of each one of these points instead of an entire voltage waveform. It can work off of each one of these pulses. So how you identify a synchronous timer, and you can, is that a number of different things. Number one, the only time that you're going to see a synchronous timer is on single phase equipment. So again, we're back to doctor's offices. If you ever work in a doctor's office, you know, step into the X-ray room of a vet clinic or something like that, you look at the control panel, you can immediately identify that it's single phase by two things. One is it's got a line compensation circuit visible on the X-ray tube or on the X-ray control panel. Okay. It says line compensation, and you know, you can make adjustments with that, which we don't really need to know about. You just need to know that this is present, and you don't do anything with it in modern machinery. and that it, evens out the fluctuations in incoming line voltage. But the other thing is that if you look at the timer control, then it's going to be two things. One is each timer setting is going to be a fraction. You don't deal with fractions, right? You deal in milliseconds or decimal points. If you look at your control panel, that's what you're reading out. But these, they're going to say 1/120th of a second, and then 1/160th of a second, and then 1/40th of a second, and then 1/30th of a second. So each timer setting is going to be on a dial. Each timer setting is going to be a multiple of 1/120th of a second. Okay, synchronous timers. Work off of the incoming line voltage waveform specific to single phase equipment for reasons I'm going to discuss here in a bit, maybe in the next section, maybe next week. So those are your synchronous waveforms. Work off of the incoming line voltage waveform. You might never see. What you do see though are your two things. One is electronic timers. That's what you typically work with on your machines, but you also work with mass timers. You might not really realize it, but you do. So when you pull into a patient's room and you set your technique, what do you set? It would be in mass, right? You don't set MA and time separately. You just set KVP and mass. So most of your timers are most of your portables, rather, at least the ones I've worked with, they had a set MA station at 100 MA, and what you actually adjusted was the time. Okay, that's what you refer to as a mass timer. You don't adjust MA and time separately. Typically, MA is set, and you adjust your time. So, if you're shooting cross table lateral of anything on a portable, you're using relatively high mass value, just kind of time it out, 1001, chances are you're working off of a 100 speed or a 100 MA system, and you're just adjusting the time. So a 100 mass exposure is 1 second exposure. 200 mass exposure, 2 second exposure. Great for, breathing techniques, things like that. You don't have to adjust your MA and your time separately. Your MA is set, and you just know what you have to deal with in time. So that's your mass time. You don't adjust MA and time separately. It's just mass all by itself. So the other one is automatic exposure control. And this is a little more complicated. AECs are realistically what you use most of the time. And if you flip over to page 102, you see the two representations of AECs. I'll talk about them individually here in a minute. But if you're taking x-rays, chest x-ray, abdomen x-rays, hips, pelvis, whatever in the department, chances are you're using AECs. Like I mentioned before, that I've worked in hospitals where we used AECs almost exclusively in hospitals where they encourage you to turn off the ACs on anything that you could. So the benefits and drawbacks to each one. The benefit of using the AECs is that you don't have to come up with mass. You don't have to remember a lot of mass values, and you don't have to estimate based on patient body habits and things like that. I'll tell you how that works here in a minute. The benefit of not using AECs is you have more positioning latitude. If you're using AECs, you have to put the anatomy of interest directly over the AECs, or you're not going to get the exposure to the interceptor that you want. Talked about that a little bit in the when we were talking about humerus. You remember talking about that? Humerus is this big, AEC's this more like the size of a cell phone, so you can't possibly cover up the entire AECs with the anatomy of interest, right? So positioning is very important if you're going to use AECs. So how they work then is you've got an orientation of AECs, and you can see them on your wall buggy, and you're going to have at least 3. You may have as many as 5. right? And all they are is radiation detectors. And again, there's a couple of different types, but they're just radiation detectors. They're kind of like photon counters. That's all they do. They're preset to receive a certain number of X-ray photons, and once they receive that number of photons, what they're going to do is they're going to send a signal over to the timer circuit to discontinue the exposure. So you put the proper anatomy over, let's say we only have 3. I'm doing a chest X-ray. For whatever reason, I'm doing an AP chest X-ray. I put my lungs directly over the ACs and make an exposure. I should get a good exposure, right? But if I off center somehow or another, and get direct exposure to one, then it's going to shut off. It's going to send the signal over the timer circuit to discontinue too quickly. So let's just pick a number. I usually use 5. Let's say these are preset to receive 5 whatever, milligray, Rinkin, whatever. You plug your unit of radiation into it, doesn't matter. It's going to receive 5 of something. Enough X-ray photons to get to that number. Okay, so I position properly and I get a proper exposure to my image receptor. It receives its 5 and it sends a signal over to the timer circuit to kill the exposure. Okay, everybody good with that so far? Okay, so now what if I have a pathology? Let's say I've got a massive pleural effusion on the left-hand side, cardiomegaly or something that, my heart is huge on the left-hand side. If I'm activating more than one AEC, then it has to read off of both of those, and it might average the amount of radiation between them before it sends a signal over. But if I've got a pathology I put over this one, then what's going to happen? It's going to do what?
Tell it to shut off before it needs to.
Exactly. Let's go backwards, the opposite direction with it. I'm going to have to absorb more X-rays. So this is going to stay on longer because I'm absorbing more X-rays. It's not receiving the X-rays because I'm absorbing more X-rays. So our exposure time is going to continue on. Our MA is set. Our exposure time is going to run longer before it sends a signal over to terminate the exposure. If it doesn't do that, then I'm going to have a situation where I'm going to underexpose the image receptor. But it's preset to receive that, so that should not happen. Right? That kind of makes sense? If I misposition then again, and I receive direct exposure to this one, how long is it going to take before this one receives maximum exposure? It's going to be quick, right? So I'm going to underexpose a patient. What if instead, I'm still taking a chest X-ray, instead of activating these 2, I activate this one. Now what am I shooting through? Instead of lungs, I'm shooting through heart, spine, sternum. A lot of stuff I don't really need to see. So it's going to take longer and I'm going to overexpose the patient. Right? So how are you going to visualize all that on your image? What's your image going to look like? It's a trick question. Really? Nothing. Right? Why is that? Well, Amy's probably walking through this right now, or if not, she's going to be walking through it before the end of the semester. The main thing that controls the appearance of your image is going to be your computer algorithm, right? So if you overexpose a patient a little bit, then the computer algorithm is going to kind of even that out a little. If you underexpose a patient a little bit, it's a little bit tougher for the computer algorithm to do so, but it's still going to compensate for what you did wrong. So does it matter which one of these we use?
Depends how you're positioned. Okay.
Why? Get a better image. Maybe the computer algorithm is probably going to spit you out a good image anyway. But what happened when we use this one? What did I give the patient?
Extra.
Way too much dose. So from an imaging standpoint, you might not see anything. From an ethical standpoint, it's vital that you understand how to manipulate these. Now, most of the time, on the machines you use, you push a button and it automatically orients these, right? But if you happen to be working in a place where you have to select these, you need to understand what it is that you need to see. Chest x-rays, you need these. L-spine, you need this. T-spine, you need this. Sternum, good luck. With sternum, you really set a technique, but you get where I'm going, right? Pelvis, you may need all three, possibly. Okay, so you need to understand how they work. Once they're set up, though, you don't do anything with time. The patient's body is what gives you the time. The patient's body and the orientation of these things is what gives you the time. So what if you make an exposure? Again, we're going to go back to humerus. And let's say I activate this one because I don't want to squat down. I activate this one and I put my humerus over it. Again, my humerus is not as big as this. So if my humerus is this big, and that's the anatomy I want to see, what am I shooting through here? Stomach's growling. I apologize. That's soft tissue, right? But is it going to absorb the same as the bone? Answer is no. Add to that position complications of, you got external rotation, so you're going to position the patient like this, right? So now you've got to figure out exactly where the bone is going to be coming across this thing in that orientation. Right? What's the likelihood that you hit that dead on? I never have. Right? So it's going to be tough. So how can you compensate for your maybe not perfect position? Okay, you set a technique. That's the best way to do it. But if you're clueless on technique, what kind of technique to set? Because you're going to have, even as a seasoned tech, you're going to have somebody that's going to throw you a curve one day. You're going to have somebody walk in and their humerus is the size of somebody's large thigh. Or you're going to have a pediatric patient that's only this tall and you need to shoot a humerus. You're going to have to come up with a technique. But in this case, how could I compensate for that? I showed you the settings downstairs last week. Remember what they were?
+1, -1?
The body habitus. The body habitus plus minus one. Exactly. So what the +1 does is, if this is preset to 5, right? If you hit +1, it might bump it up to 6.5. If you bump it up to +2 or use, the second body habitus up, it might bump it up to maybe 8, something like that. Okay? So that's how you compensate using automatic exposure controls. Is you can adjust those. And it's like it's recalibrating the photocells so that, you compensate for your missed position. And that's what those things do, is it recalibrates those and tells the photocell to give me more radiation before you terminate the exposure. Still operate the same way, still get that amount of radiation exposure that you set, and as soon as it does, it sends a signal over the timer circuit and it terminates the exposure. Clear as mud? Okay, so the reason I wanted to get that in before we took a break is because voltage rectification is a little bit complicated too. So if you look on page 102, you'll see the different types of phototimers. So you have one is ionization chamber, and that comes that's before the image receptor. Okay, so both of these are in the bucket. All right, so you got two different types. One comes before the image receptor, and one comes after the image receptor. Photodiode is after the image receptor. So anything you put in between the patient and the image receptor, remembering that everything is some degree of radiolucency, right? Or it's radiopaque. What would the the characteristic of the ionization chamber have to be, if you're gonna put it between the patient and the image receptor,
Radiolucent.
it's gonna have to be very radiolucent. Got a little bit more flexibility with photodiode, but the ionization chambers have to be very radiolucent. Otherwise, you're gonna have artifacts on every image that you shoot. Okay. Questions on that? Questions on anything about that?
What button was that? What button did you do?
To control that, the ones that you remember, probably still have the picture, but the ones that look like different body habits or different patient size, wasn't really body habits.
Little person and big person?
Bingo,
Oh.
bingo. So that 8 might be, you know, the biggest person. And then if you hit the littlest person, it might drop down to 4 or 3 or something like that. Or your machine may have +1, -1, and that does the same thing.
So what would you call those timers?
These?
Yeah.
Automatic exposure control. You're gonna hear them referred to probably most commonly as autotimers. Or AECs, just short that. Which guy?
Where are those? Like if you're trying to line up, you know, like different keymines or something, where
There,
do you see those?
you should see squares and circles on the wall bucky. On the table, you're not gonna see because the table moves everywhere. But on the wall bucky, you know, the bucky doesn't, the cover on the bucky doesn't change, right? So next time you're in clinicals or if you're in lab, take a look at the bucky and you should see circles or squares, and that's what those represent, is where those are. Anything else? I thought we might get through the chapter today. We're not going to, and I don't think that, you know, we could talk about the voltage rectification, but that would make Wednesday's lecture like 20 minutes. So why don't we save voltage rectification? Plus, it's kind of complicated. You know, I just threw something kind of complicated at you. So